Super-Rosenbluth experiments. All right, take it away, Axel.
Thank you very much, Ethan, and thank you very much for all the organizers for inviting me and reaching out to me to participate in this, which you can bet I wish I were in Trento right now. This was a wonderful excuse to investigate a piece of what I would call folk wisdom, that radiative corrections are smaller and simpler in so-called Super-Rosenbluth experiments. And to refresh everybody what I mean by Super-Rosenbluth, or at least clarify the notation, the problem I'm specifically interested in is electron-proton elastic scattering, where the kinematics are we send electron beam in on a fixed proton target. We've got a scattered electron, a recoiling proton, and the conventional experiment would be to put a spectrometer or detect the scattered electron. The so-called Super-Rosenbluth approach is to put a spectrometer to detect only the recoiling proton. And I've never done one of these experiments, so I don't have a lot of inside knowledge about what goes through one's head when one's running one, but I've heard this claim repeated that the radiative corrections get simpler. And I had occasion to try to investigate this about a year ago and got some very weird results. And this dug me down a rabbit hole, and I wanted to share with you some of the follow-up about this that I've explored. So why would I at all be interested in this? So just a little bit about my history. I did my PhD on the Olympus experiment, which has been mentioned a bunch of times in this workshop so far. And Olympus investigated hard two-photon exchange and elastic scattering by comparing positron proton cross-sections to electron proton cross-sections. And as part of the team on that experiment, I worked with Jan Bernauer, Rebecca Russell to develop the radiative generator that we ended up using. After Olympus, I moved to a postdoc where I started, oh yeah, here's our results. And what we basically showed is that the amount of hard two-photon exchange is less than we'd expect in the kinematics that we could access. After work on Olympus, I moved to a postdoc working on experiments at Jefferson Lab, and I haven't left. I'm currently working on a number of Jefferson Lab experiments. I'm a member of CLASS and GLUEX, and primarily my interests are studying the role of nucleon-nucleon correlations in a number of different nuclear phenomena, the EMC effect included. And part of my work, I built the class 12 backward angle neutron detector. I've been worried about these nucleon-nucleon correlation issues, and I've gotten a little bit out of the field of radiative corrections. So I'm doing this work as a bit of an amateur. What pulled me back in a little bit is being involved in the Jefferson Lab positron working group. And this group of physicists were advocating that the future of Jefferson Lab should involve building a source to put positrons into CBAF. And there's all sorts of physics. And for me, obviously, the interest is to tackle issues of radiative corrections, two-photon exchange. Now, we just made a white paper that was published as a special issue of the European Physical Journal, and I invite you to check it out. It's a lot of work from a lot of people went into this, and I think we make a really strong case for why Jefferson Lab should go this route of building a positron source. Okay, but this white paper specifically is what made me interested in Super-Rosenbluth experiments, because as part of this is mocking up experiments that involved using the Super-Rosenbluth technique or using proton detection as a technique, and looked at some radiative corrections things with this wisdom that they would somehow be simpler, and I got some weird results. And so to set the stage, in a conventional experiment, you have the spectrometer detecting the scattered electron. And as this has been done all the way from Hofstadter's time out to the Mainz measurements, this is the conventional approach, and radiative corrections developed conventional approaches to deal with this kind of experiment. And so we have radiative corrections formula like Mo and Psi. There's all sorts of technical improvements beyond the soft photon approximation, a number of them we're hearing about now. This is a well-studied problem. You could also put another detector and catch the proton. That would be a coincidence experiment. And for example, Olympus, my PhD experiment, was a coincidence measurement. And there, because you're making cuts that depend both on electron kinematics and proton kinematics, I think the approach to radiative corrections is almost universally build some model into a radiative Monte Carlo generator, apply coincidence cuts to the simulated data, and perform radiative corrections that way. Or instead of radiative corrections, you're doing simulating radiation. Now, in the case of Super-Rosenbluth, you take away the electron detector, and this, for example, is the flagship measurement I'm aware of, was done in Jefferson Lab Hall A. It was published in PRL under Catan et al. In 2005. Now, how do you deal with radiative corrections here? I didn't know about any particular formula. It turns out there are some. But if one tries to take the approach of simulating radiative effects, one has the problem that they have to integrate over all possible electron phase space, because you aren't detecting the electron. And that means you have to, and because the electron is primarily the radiator, that means you have to handle radiation all the way down to the electron losing all of its energy, which is, that's a big integral. That's a big phase space to cover, and you got to get the whole phase space accurate. Now, I should point as a caveat, Andre studied this and he sent me his paper yesterday. I just learned about this paper. And so I've linked it here. And embarrassingly enough, it seems to answer a lot of the questions I raised today. So well done, Andre, for solving this problem 20 years ago. I haven't coded some of the equations in this paper yet, because I think they would bear quite a lot of relevance to the calculations I'll show today with other approaches. But it's something I'd like to do, and I hopefully can maybe provide some follow-up. If we write a proceedings or a white paper, I should have it done by then. Okay, so why do Super-Rosenbluth? It does have experimental advantages. And so I'm going to just give an example by looking at a conventional Rosenbluth. So here's another JLAB measurement that was done in the early 2000s. Let's say you want to extract the form factors of the proton at q² at 2.75. What one does is measure the absolute cross-section for elastic scattering, where you keep q² fixed, you vary epsilon, you get data something like this when you divide out the structureless part, and we call it the reduced cross-section. You can fit a line to this, and in fitting a line, the intercept of that tells you something about gm², the slope of that tells you something about ge². Now, if you do this with proton detection and you keep q² fixed, that means that the outgoing proton momentum doesn't change as you swing around in epsilon. So you might have a high epsilon point like this, and you might measure a medium epsilon point, you might measure a low epsilon point, but you notice that the magnitude of the proton momentum stays fixed the entire time. Now, experimentally, that has a very nice systematic effect, is that you're not mucking with the spectrometer optics. So if you want to calibrate the optics in one place, you get it all set, you spend your time doing the calibration, you don't touch the spectrometer magnetic fields, and then you can move the spectrometer around to do your Rosenbluth separation. So I think there's some very good experimental reasons why you can reduce systematics by using this technique. The key flagship measurement, as I said, is published in PRL in 2005, IA Catan et al. It was an experiment that was done in Jefferson Labs Hall A. And so it was using the high resolution spectrometers. These are 23-meter flight path, QQ, DQ, 45-degree bend spectrometers. They got a momentum resolution 10⁻⁴, it's about 6 millisteradians of acceptance. And in this experiment, they did 5 beam energies to try to do Super-Rosenbluths at 3 different q²s. And so I thought this would be a good excuse to try to repeat these kinematics and sort of use this as my model experiment. In this paper, they have a couple of very tantalizing lines, and I will put them up for you to read. Okay, so the claim is smaller epsilon dependence for radiative corrections. And the second claim they make in the paper is this. Okay, so the two claims are, when doing proton detection, the Super-Rosenbluth technique, radiative corrections are both smaller and their epsilon dependence is less. And they don't back this up. They don't show any graphs or any, I mean, it's a PRL. They don't have a ton of space to do so. But I've always been curious about this, and I assumed it was true, but in doing some of my own calculations, saw some weird things. And so it's worth digging into this a little bit further. So what radiative corrections did they use in their experiment? their radiative corrections trace their way back to radiative corrections developed by the NE18 collaboration at SLAC. This paper is, the first author is Ralph Ent, but it's a number of theorists and people at Caltech and MIT that conducted this experiment. And the reason that they use this is because this, the Monte Carlo approach in the back of this paper that was imported into the software SimC, which is widely used at JLab. And this is almost the default radiative correction approach one does in elastic scattering or quasi-elastic scattering. So what does this generator do? Well, it does multi-photon emission. So it's in some sense exponentiated. You are not looking at one photon, but you're looking at the total energy released by all photons. It's multi-photon, but it's purely peaking. So the radiation is emitted in the direction of the incoming beam. It's emitted in the direction of the outgoing lepton, and they also have a term for radiation emitted by the outgoing proton. And they will randomly sample radiation from each particle that update the kinematics at each step. And it does handle the loop corrections, the vertex, the electron vertex, the vacuum polarization, soft two-photon exchange. That is in there, and it's non-exponentiated according to this procedure. Well, it turns out I've got a working implementation of this. Let's fire it up and see what happens. So I did a simulated pseudo experiment, same Q-squareds, and I just get a good spread in epsilon. And I imagined a spectrometer that's got very, very small in-plane acceptance. I don't want any acceptance. I don't want any like large acceptance effects to be mucking things up. I said, okay, let's have a millirad detector. So it's much smaller than Hall A, and just assume standard dipole form factors for the sake of simplicity. And let's see what we get. Okay, so run the generator and now make restrictions on detecting the proton and then integrate over electrons losing up to all of their energy. And so I can get a tail shape, and I can do this experiment where I do electron detection, or I can do this with proton detection. And sure enough, I get decent tails. I can integrate these tails to get a total yield depending on where I put my elastic cutoff. And that then I normalize that by the Born cross-section to get a radiative correction. And so here's the radiative correction I see for this particular Q-squared point, for this particular epsilon point, as a function of where I put the cutoff in momentum for what is defined as elastic. And so one claim is that the radiative correction is smaller when you detect the proton. Now remember, we're smaller here, I guess, means closer to 1. So the effect of the change relative to this multiplicative correction being closer to 1 means a smaller correction. And I would want to point out there's a turnover point. It's very, very far away from the elastic peak, a whole 100 MeV off, but at some point the proton correction turns over, and it's farther from 1 than the electron correction. So, I think what they mean for the kinematics they're looking at, it's closer to 1, but that's kinematic dependent. You can also look at different Q-squareds in some, and also point out maybe it's more fair to compare, instead of comparing absolute momentum, comparing relative momentum, and that just shifts things around a little bit. So it's all kinematics dependent. You can change Q-squared, and in some cases that cutoff point shifts to smaller momentum, and you can look at other kinematics and it shifts way out to further momentum. So in some degree their claim is true, in some degree it's a little bit kind of where you're looking at in what kind of cutoff point you choose for your experiment, but okay, that's fair. In any case, I do want to point out that regardless of the kinematics you look at, here's a spread of 4, the proton tail is definitely flatter in momentum than the electron tail. So already that's makes things better, right? You're less sensitive to the exact cutoff point than if you were to detect the electron.
Axel, can I ask a question?
Yes, can you get the microphone? It's hard to hear you.
Yep, I'm bringing it over to Jan.
Okay, great, perfect.
So naively, I would have expected that they converge to the same value if your cutoff goes to infinity, because then you integrate over all momentum in both cases. Or do you have then an acceptance effect in the angle?
Great question. I hadn't thought about that. I mean, I understand your argument. Clearly, that's not what the data show. I mean, unless some weird stuff happens and the proton turns over it crazy.
Yeah,
Can you
I mean,
please repeat the question?
The question was, oh, go ahead, Ian.
yeah. So if you do not have a cutoff, right? If you make your cutoff arbitrarily large, it should be the same correction, right? You measure the same cross section, the total number of particles. Or is that actually maybe not true?
There's a factor of 2 difference. I mean, proton cross section tends to, because you're measuring a differential cross section.
Sure. Yeah.
But you're talking about the correction to that cross section.
Right. So.
But I guess there's a misunderstanding here in terms of what is epsilon. Epsilon is made by the electron arm. If you
Sure.
measure the proton, then you get the right Q square, but you don't care where the electron goes. And if you have initial state radiation.
Oh yeah, right. It's a different integral. Yeah, you're measuring a different cross section. Yeah. It's a different integral over the angles. Yeah,
I understood the
right.
comment, but I could not tell who made the comment.
That was the other Jan.
Jan, that's a fantastic comment. That's yeah, that totally makes sense.
Yeah, that's right. Right. Okay, thank you.
All right. Let's investigate claim number 2, which is
Axel, sorry,
another
1 second.
Please.
Ron has a question.
yes.
I think I have a comment. I'm not sure I remember this correctly, but my memory is that one of the experimental benefits of Super-Rosenbluth was that when you measure the scattered electrons, the rate in the electron spectrometer changes by orders of magnitude when you go from high to low epsilon points, whereas the rate in the proton spectrometer doesn't change by nearly as much. So it's
That's another, yeah.
so
Thank you for that.
Okay.
The other comment that I was shocked, and I can't believe I meant to include that slide, and I guess apparently that graphic didn't make it into my beamer, is that what I did not consider is that when you put a proton spectrometer forward to get these low epsilon points, you're also putting it right to the spray of all this other junk from other processes. I could not believe, I'm used to thinking of elastic scattering as very clean, but in this paper, they show their proton spectrum, and it's sitting on top of a huge and asymmetric background that they had to model to get the proton elastics out from on top of this other background. And this should have been in the presentation, and I'll show it maybe after and as we do Q&A. So that was an unexpected experimental challenge. But I mean, apparently the agreement between their data and Monte Carlo looked really good. So it's fascinating how many things it changes that I certainly didn't expect, having never done this. Okay, so then let's look at epsilon dependence. So here's what you would do for a conventional Rosenbluth electron detection: the radiative correction size as a function of epsilon for a particular fixed Q squared, as a function of where you put the delta P cutoff. And so if you make the cutoff smaller, your correction factor gets bigger, but maybe the slope in epsilon gets a little bit smaller. Anyway, this is the landscape you're looking at for electron detection. If you then switch and do the experiment in proton detection, here's what you get. Definitely flatter, definitely less epsilon dependent. So I can toggle back and forth again. So electron detection and then proton detection. It's definitely smaller in epsilon. You can do this with the different Q squared. Let's crank it up to Q squared of 4. Here's the electron experiment. Here's the proton experiment. Again, definitely flatter in epsilon. So all this to say, the conclusion is 2 claims are made in this paper. First, that the corrections themselves are smaller. I think that's a little bit kinematic dependent, but I'd say that's true for the kinematics they're looking at. And then second, radiative corrections are less epsilon dependent. That's definitely true within their chosen radiative corrections prescription. So within the approach they're using, these claims totally reasonable. So that's nice to validate. That was reassuring. But what happens if we try to do this in a different prescription? And the one that I'm kind of curious about is the Olympus radiative correction radiative generator, because I worked on that. So I tried it with that. And here's a quick review of what we do there. So we really had a couple generators in one, but I want to say that we used two primary approaches in order to compare them. And what we were interested in comparing is the effect of exponentiation, effect of trying to treat multi-photon emission. And so we had two approaches. One is the conventional approach where we just looked at alpha to the third power. And in this approach, what we do is we distinguish between near elastic and tail. And so in near elastic, we can just use a standard formula that is rejiggled to set the cutoff variable in the amount of energy radiated rather than in, say, the amount of energy lost by the electron, because we are doing a coincidence measurement. And then so that covers the near elastic, that's well under control and then in the tail, we just use the tree level Bremsstrahlung cross section. And we are treating all four diagrams. None of this, well, the initial proton is stationary, so it doesn't radiate. That we're doing the proper all four diagrams, get the matrix element, square it, get the cross section. Okay, so that's the conventional approach. The exponentiated approach is based on previous work by Jan Friedrich and Jan Bernauer. It was developed at Mainz A1. We extended it a little bit to try to make it do some things that we needed for Olympus. And basically, it does exponentiation under a couple of different assumptions. First is that the multi-photon kinematics are pretty much well approximated by single photon Bremsstrahlung kinematics, that the differential cross-section will take an exponentiated form, and that the differential part of that form is well approximated by the tree level Bremsstrahlung. And then the last bit is the correction of that is given by a standard formula, for example, Moenstein. So it ends up being extremely similar for almost everything to the conventional approach. It gave us about a % difference about a % difference in the ratio of positron proton to electron proton cross sections at the end of the day when we compared approaches. So here's what I got when I tried to do the same Super-Rosenbluth experiment with the Olympus generator, and it looks awful. And there's definitely a numerical instability going on. And this is this result is more than a year old, and I was totally stumped by this. And finally, this month, had a chance to dig into this in advance of this workshop. The craziest thing is that if you turn off emission from the proton, the numerical instability goes away. And that was a very weird lead to find. I did not expect that. So what's going on here? Ask the question, where do the electrons go for protons that go through the correct angle with the correct momentum? And this is essentially the electron phase space. So electron scattering angle is on the x-axis, the electron momentum's on the y-axis, and you can see this big bright spot here at about 60 degrees and 1300 MeV. That's where electrons should be going if they were elastic. And so you can see this stripe vertical, that's the final state radiation stripe. So that looks all good. But the stuff that's high weight events with a lot of variability is for electrons going very, very soft and very, very forward. And so then this prompted me to start looking at all of the denominators of all the propagators and all the diagrams and figuring out just numerically what their values were. And I've sort of hit on where the numerical instability is coming from in this generator. And this is the scenario. Electron comes in, it loses all of its energy into a virtual photon that's going forward, essentially going the direction of the beam. This has Q squared very, very close to 0. It then essentially Compton scatters from the proton. So the proton will emit, and it will not emit a collinear photon. It will emit a photon where the electron was supposed to go. Now, you can say, what on earth is the cross-section for this? And what it looks like is all the propagators in this approach seem to be finite, and they're not big, but they are finite. And then because this Q squared of this first virtual photon goes to 0, this blows up. This is the source of the instability. So I'll call this barely virtual Compton scattering. And I don't know if this is repairable or how to repair it, other than it looks like Andre solved this and was able to do this integral. And so I think this needs to be analytically canceled in some way that our generator just wasn't aware of and didn't take the pains to do, which is, I mean, that wasn't the goal of this generator. So that's totally fine. So I think if we wanted to build a generator to do Super-Rosenbluth, we'd have to go back and really handle this, this instability issue to try to make this work. So to recap, that's all I just wanted to say today. So first point is Super-Rosenbluth radiative corrections have this challenge that you have to integrate radiation from the electron essentially all the way down to zero. And so that's very, very different than most radiative correction situations where you're trying to look in a region near some elastic peak or near the kinematics of interest. Second, within the peaking framework that of the NE18 and SIMC, Super-Rosenbluth radiative corrections are smaller and flatter per the claims made by the paper from the Hall A experiment. So I think that's within that framework, totally valid. Lastly, there are numerical pitfalls for the full Bremsstrahlung cross-section that one has to be aware of. And it's not, obviously, I spent a lot of time working with Jan to take the generator that other Jan developed to make it good and stable, and obviously totally missed this because I wasn't aware of it. And what I would conclude from all of this study is that until I get a second model working, I have no clue about the model dependence of the SIMC approach used in Hall A. I don't know. It may be that these radiative corrections are really robust and they get the same value in all models. I suspect they probably won't be. I expect you do this integral with a more serious Bremsstrahlung calculation, it may shift the radiative corrections a little bit. So if I get a second model working and get Andre's paper coded up, I'm definitely curious to see how much the radiative corrections would change. And then, yeah, credit to Andre for solving this 20 years ago. And thank you for sending me the paper. So I've got some interesting reading and homework to do.